for some variables. Okay, all of these are really similar in their setups. They differ by just a little bit, but not by much. So when we go ahead and take a look at this, we're going to go ahead and give you an equation. You'll never have to memorize equations. You'll always be given it. You just have to be able to use it to solve for your answer. Okay. So the first one is we're going to have is pressure times a volume is going to equal another pressure times its volume. Okay. So basically, the calculation you'd have to do within a sample of a closed system, if you change the volume in any way, the pressure will change inversely to that. I can give you an example here, okay, without numbers. Sometimes it's easier to look at numbers or examples here real quick and easy. So let's say I put let's say that we have a pressure, and we're going to say that it's a pressure that's 1. And let's say the volume is 2. Okay? So then, let's say that we reduce the volume to 1, which is half as much, right? So let's say that this is 2 liters. Reduce it to 1 liter. And the pressure, let's say, is 1 atmosphere. What's the new pressure going to be? 2. Because they have to equal one another, right? So 1 times 2 is 2. 1 times what has to give you 2? And of course, that would be 2 atmospheres. So when you look at that, it is inversely proportional because I've cut the volume in half. So that means the other thing has to invert. So what's 1/2 inverted? 2/1, right? That's why it's called an inverse relationship. Is that when you change one in a certain way, the other one will change also. So I'm going to give you a word problem here real quick. And then what I want you to do is I want you to, now, a lot of times what we'll do is we'll label this. We need to differentiate between these pressure and volumes and these pressure and volumes. So what we do is we just say 1, 1, 2, 2. Okay, and that's the equation that we're going to use. Is that equation right there. So I'm going to go ahead and give you a word problem real quick. Then what we want to do is we want to identify all our variables. And I would like to see you write these out. They just take a very short period of time, and it helps you organize your information. And like if it's a word problem or something, it helps you organize your information. So I'm going to go ahead and give you a word type of problem that you got to pick out these different variables and find out what you need to solve for. Okay? Okay, so when a cylinder has a beginning volume of 80 milliliters and a pressure of 2.2 atmospheres, and the new volume is reduced, not 13, is reduced to 8.5 milliliters, what is the pressure? So let's just go through and label everything. So a lot of times P1 is like an initial, what you're starting with. Okay, or I'm going to say 1. I shouldn't say P1, but 1 means initial, and 2 means final. Okay, so what would be P1? 2.2. So right here is P1. So 2.2. Okay. V1, do we have that?
Yes.
What is that? 80. Now, when you do these problems, the volume can be in anything, as long as it's the same before and after. Okay, so it can be milliliters, centimeters cubed, liters, anything along the line. P2, which one is P2? So this is V1. So what is P2? What's that?
We don't have it.
We don't have it, right. So that's one we got to solve for. And then V2. Okay, so before I even do this problem, I should have an idea what the number realistically is. This is a lot of times students have a hard time with this, to visually look, okay, what should it change and how should it change before they even do the problem. So you look at this and go, okay, the volume's been reduced by a lot. Okay, it's been reduced by a ton, 80 to 8.5. What should happen to pressure? Should go up a lot. Okay, it should be a lot, Chet. So, this is about, do you guys see about that this is about 1/10? A lot of times I'll always look at, well, how do they compare? 8.5 goes into 80, not quite 10 times, right? Between 9 and 10 times, right? So if it's an inverse relationship and it's reduced to about 1/10, what should the pressure do? Go up by 10. So I should be looking for an answer this times 10. Not quite. So anybody want to guess what it'd be? 20 point, somebody said 20.7. Okay, so we should have a lot of times we should have an idea about what it turns out to be. So what I'm going to have you do is, what I want you to do, I want you to take this equation here, okay? And what I want you to do is I want you to solve I want you to go ahead and solve for the new pressure. Go ahead and do that. Use your algebra skills. You're going to solve for P2. So go ahead and do that. I want to see if you can do that. You should. Everybody in here has that ability. When you sign up for chemistry, we look at what you've taken, math, and it says math, you've taken, at least up through this math class, and so you should be able to isolate variables and solve for them. So go ahead and do that and solve for the answer. I want the exact answer. So we know it's going to probably be in the low 20s. So go ahead and do that. So, again, final setup is like this. Solve for the variables and then plug your numbers in. Don't plug your numbers in and then move your numbers around because, again, they get you get two volumes and two pressures and two temperatures. Sometimes that becomes a little bit tougher to do. Okay? I don't want to do this law yet, so I've got to figure out which law I need to do. Not that law either. Okay, I'm going to do a little racing here. So, this is the next law. You go ahead and write that out. Every law you have to know a little bit about. Okay, so this is Charles' law. we did not, you guys did not investigate this one. There is an investigation that goes with it, but it doesn't really turn out very good, and it's kind of a neat one to do, but it takes a long time. Plus, we've done some relationships similar to this, and so Charles' law says if you look at temperature and volume, they're going to be directly proportional to one another. Directly means they change in the same change in the same direction. So when I give you this formula, okay, it's going to be V1 over T1 instead of V1 and P1 times. This is direct, and so I'll explain why it's written like this. So it's like if I have temperature down here and volume over here. You don't have to write this part down, but I have volume over there. And I do my plots. I say as the temperature changes, it's going up. It's like the balloon. It gets bigger. It gets hotter. We measure it. We calculate the volume using equations. And then what we get is a line, a best fit. So when volume goes up, what happens to temperature? It goes up. So going to the right, it increases. If this goes up, more temperature, then volume goes up. Vice versa, if temperature goes down, volume goes down. Okay? So what do we call this here when you take the rise over the run? Slope. All this is an equation for the slope. That's all it is. Okay? So some of you, like y equals I think mx plus b, or ax plus b. Guess what? That's a direct relationship. All of these, the rest of these that I'm going to show you are direct relationships. So, I want to make it easy for you guys to do. And I will guarantee, if I gave a problem and you had to solve for T2, I've given all these other variables like at the previous problem, you guys, half of you won't get it right. Okay? Because you have trouble, it's just the facts that I've seen, you have trouble solving for a variable that's in the denominator. There's too many steps, and you don't do the steps right. Okay, so this is what do they do in math to simplify this? Is there something, a technique you can do to simplify this before I start rearranging the symbols? Is there anything you do with ratios? When you guys do with ratios, is there a way you simplify that and make it and change it around so it's easier to work with? No? You guys have heard of cross multiplying, right? Yeah. So if I cross multiply this, what will it look? Because it's just a different way to look at the equation to solve for the variables. So if I cross multiply this, what's it going to look like?
T2 times V1.
Yep, T2 times V1 equals...
T1 times V2.
Yeah. Now, invariably what will happen, students will get in a rush or they get going, and guess what they'll always write this law, they'll write it wrong. And they'll write it wrong because what do you think they'll write in place of this instead of what's there? They'll get it confused with this one here. So this is a common mistake students do. When they write this out to solve for it, what do you think they'll do? They'll have T1 times V1 equals T2 times V2. That's direct relationship. It's not even that. So something to remember when you do these, the T is always opposite of the V or the P when we do them. The T is always opposite. It's never going to be the same when it's multiplied on one side of the equation. So keep that in mind. You go, oh, I better not set it up like that and get it wrong because I got T1 and V1 on the same side multiplying. That can't happen because they're directly proportional. Okay? So questions on that? All right, I'm not going to do a problem with that, I will, yeah, we better do it. But I'm going to give it to you, not as a word problem. I'm just going to give you the variables, and then I'm going to have you solve for it. Okay? So I'm going to go ahead and give you all the variables except for one, and I'll have you solve for the one. Okay? So we'll go V1, T1, oops, V2, T2. So I'll go ahead and give you 2 liters, temperature of 20 degrees Celsius, volume that is 0.5 liters, and then I'm going to solve for the temperature. Okay. So before you do this, there's something you have to do to one of these numbers on the left side. One of these numbers on the left side, you're going to have to do something to one of them before you can plug it into your equation. So what do you think you have to do with one of these numbers before you plug it in? Convert Celsius. You have to every time, because if you don't, so what happens? Volume goes down to be 1/4 the amount, right? You guys see that?
Yeah.
Everybody see it's 1/4. So temperature should go down what? 1/4. So if I left it Celsius, guess what the temperature would be here? 5. It's not 5. It doesn't change that much. 15 degrees, something going from like this to this, 15 degrees. So you have to change this. This is a naughty word in doing gas laws. This is a naughty word. Don't ever, ever say Celsius when doing gas laws. Okay? This would be what then?
293.
Yeah, 293.15, but since this only goes to the nearest one place, I can just make it 293 Kelvin. So go ahead and solve for the temperature. We know it's going to be lower. Every year on tests, I'll have 1 or 2 people, and I think these 1 or 2 people, they don't do their own work. Because if they were doing their own work, they would be doing Kelvin, and they would be getting it right. Invariably, what will happen on tests, every single problem that people leave it in Celsius, and they get every single problem wrong. Okay? Don't be one of those people that leave it in Celsius. Okay? What I would do on a test, every single problem that had Celsius, I would automatically change it to Kelvin. I'd go through the test, change everything to Kelvin, and then I don't forget. Okay, so this would be T2 equals T1 times V2 over V1, right? Because I divide both sides by V1 and get it. So that would be, and then I can go, now make a mistake, 293 Kelvin. V2, 0.5. V1, 2 liters. There we go. Okay? I have to do that too. I make mistakes too. I look at a word problem or something and I think, oh, I'm going to put this temperature in, but I invariably put the wrong temperature in. And it messes things up. It does the opposite of what I want it to do. It goes the opposite direction as what it's supposed to when I take a look at changes. 73, right? 73 Kelvin. That would be a minus 200 degrees Celsius. So to reduce the volume, it would be a minus 200 degrees Celsius. That's like the temperature of nitrogen, liquid nitrogen. Okay? So 73 Kelvin. Any questions? Okay, I got these last two will go really quick because they're directly related like this one is. Okay, same concept, you write them out. We know units. Units for volume is liter, milliliter, centimeters cubed. We know pressures, atmospheres. Okay? So Gay-Lussac's. This is the one you guys investigated. If you guys took a flask and had it hooked up to a pressure probe and you put it in hot and cold water, guess what? it formed a direct proportion. Right here. See the direct proportion? You got it. See the inverse proportion on the left side? Okay? That's Boyle's law. This is Gay-Lussac's law. Okay? That you're proving. Okay? Before you even knew what it was, you figured out the relationship already. Okay? So, on the right side it says, when the temperature decreases, the pressure decreases. And so that's inverse. And on the left side, it says smaller volume, the pressure increases. That's what those laws say. Okay? So we're not going to do a problem on this one. But if it's directly proportional, how should it be written? P1, where should be T1? Times or divided? Divided. T1 equals P2 over T2. And to simplify it, you would just cross multiply. So I'll leave that up to you when you get to those problems. It just allows you specifically to solve for those a little bit easier. Questions? Okay. So the one thing yesterday I pulled out the vacuum tube and I put a balloon in there and we took air out, and we know when we took air out what happens to the pressure. It decreases. And the volume also will change. So what we're going to look at volume versus moles, and it's called Avogadro's law, and it's the last one we'll look at. Okay? And again, all these are really similar when you set them up. Here's Avogadro's law. N represents moles. So when you see N, that's moles. Like you guys look up there, it says gas law, PV equals nRT. See that little N? That's moles. So anytime you see a little N, V is volume, T is temperature, P is pressure. Anytime you see an N. Now, what if I have a problem that says grams, and I need to use moles? You should be able to convert to moles. Yep.
Is that an OL or a D? On Avogadro or something.
Avogadro's? Where are we
Is that a
looking
D?
at? This one?
Yeah.
Gadro.
You're missing a D. I'm calling it Avogadro. Can't stop.
Yeah.
Okay.
Amadeus Avogadro. And we had a day, mole day. You guys remember mole day?
Yeah.
Okay. So, it was based upon Avogadro's number, 6.02 to the 23rd, and that's equal to 1 mole. So, it just makes sense that he looked at relationship here between moles and volume, and he did a lot of work with gases, and this is probably where that relationship kind of come in, looking at moles and amount of particles. So, I've got a story problem for you to do. The last one I'm going to have you do. Okay? And I'm going to have you use the skills that we went through on the other ones in which to prove and come up with an answer. Okay? So this is directly related. If you double the number of moles, keeping pressure constant, the volume will double. If you reduce the number of moles to half, the volume will be cut in half. That's common relationships associated with that. Okay? So, you don't write this out. Don't write the word problem out. All I want you to do is use that with this equation and solve for what it's asking for. I'll give you a couple minutes. So go ahead and solve.
How you doing?
remember, when we do these do these tests, you guys are always given the equations. Okay, you're automatically given the equations to do all of them, so that makes it a little bit easier too. Okay? And make sure you guys get the assignment written out.